Welcome to the second lecture of automotive engineering, automotive technology rather. Today we are going to learn about fundamental thermodynamics. You did fundamental thermodynamics in the first year, but this is an advancement of the topic. So today we are going to learn about how heat engines work and how heat pumps work, and we will talk about the Kelvin Planck statement. So, for example, in your first year, you learned the first law of thermodynamics, but you didn't do anything. So, what the first law of thermodynamics just talks about is about the about heat, work, and internal energy. But it doesn't tell you much about the direction of heat flow. So the direction of heat flow is discussed in second law of thermodynamics. So we will talk about the Kelvin Planck statement. Then we'll try to understand what is meant by the Carnot cycle, and we'll talk about ideal thermal efficiency and entropy as well. So so you are strongly advised to go through the first year work as well. So we were talking about non-flow processes, steady flow energy equation, continuity equation, as well as gas laws, and that is and a lot about steam tables that you need to know in this subject. But those were the topics in the first first year work. So you were talking about non-flow processes. Now these are notes from the first year notes that you need to know. So these give you the fundamentals of basically processes, process laws, work done, added, etc. Okay. Then you talked about the steady flow energy equation. So for an open system, so basically for a closed system, you had non-flow process for a closed system and steady flow energy equation for a for an open system. So for a open system, Q minus W is so that's the energy equation, basically steady flow energy equation. And then for gas for all gas processes, you talk about enthalpy for and enthalpy can be stated with temperatures in steady flow energy equation. So, and then you talked about gas laws. PV equals MRT, P1V1 over T1 is equal to P2V2 over T2. So these are things that you wanted to know. So this is a question for you. So think about it, and this is from the first law, and think of for yourself the answer, and you will see what it is. It's actually U equals Q minus W. Okay. And then for the second law of thermodynamics, the background, I'm going to talk about the background. So if you have a hot object and a cold surroundings, now this is the object, these are the surroundings. So if the surroundings is cold, if surroundings are cold, the heat can only flow from the hot object to the surroundings. It can't travel, or it can't transfer from the cold surroundings to the hot object without us doing anything to do it. Okay. The natural flow of heat transfer is from the hot object to the cold surroundings. So that direction of heat flow is not explained in the first law of thermodynamics. It's actually governed by the second law of thermodynamics. So what it says is and then if you for example, if you have an atmosphere, where the temperature is dropping. So but this cannot happen. So the atmosphere which is of the atmosphere which is at lower temperature than the kettle, the atmosphere can't just heat the kettle without you doing anything to it. So in the first law process, the direction of heat flow is not explained. In the second law, the direction of heat flow is explained. If the direction of heat flow law is violated, it is explained. It can be explained with what you call the property entropy. Okay. So a process cannot occur if that process does not, if the first law as well as the second law of thermodynamics. So for a process to happen, it has to satisfy first law of thermodynamics and second law of thermodynamics. So we talk about what are called thermal energy reservoirs. So suppose this is a hot reservoir and that's a cold reservoir, and heat will transfer from a hot reservoir to a cold reservoir only naturally, where T1 is greater than T2 in here, and this cannot happen. Heat cannot naturally transfer from a cold reservoir to a hot reservoir. Okay, and so Clausius said no process is possible whose sole result is the transfer of heat from a cooler to a hotter body. So that is what I explained earlier was said by Clausius. He was a German scientist, one of the founders of first principles of thermodynamics. So a heat engine, it will operate between two thermodynamic reservoirs, like earlier, a hot reservoir and a cold reservoir. So when you have a hot reservoir and when you have a cold reservoir, heat will transfer from the hot to the cold. And if you put something in between, that's an engine. That engine will draw some heat from the hot reservoir and reject some heat to the cold reservoir, and it will do some work as well. Okay, so it will convert part of the heat energy that was drawn from the hot reservoir to work, but at the same time it rejects some heat to the cold reservoir, and this will operate in a cycle. So an example of a heat engine is the internal combustion engine. Okay. And then we define something called the efficiency, thermal efficiency. Thermal efficiency is the work that you obtain divided by the input that you gave. Okay, so if you got a work here from the heat engine, work output, and if you input something into the engine, that you divide the work output by that heat input quantity. So your thermal efficiency is W net over QH, and from the first law, W net equals QH minus QL. That means your W net is equal to that minus that, and this W net cannot be equal, this QL cannot be equal to 0. Okay, so you can say that your eta thermal is 1 minus QL over QH, QL over QH, 1 minus QL over QH. Right? And this is an example, heat engine example. You have a QH, that is the heat supplied to the boiler, and then you have, the condenser will reject some heat, that is QL. So your turbine gives you a W out, and then you have a pump that is driving the system. So your W net is this W out minus W in. That will be equal to QH minus QL. Okay. So something that you can do is, so if you have a 600 megawatt steam power plant, which is cooled by a nearby river, as a thermal efficient, and if it has a thermal efficiency 40%, you can you determine the heat transfer to the river? So how you do this is, okay, 600 megawatt steam power plant means that is your W net. So your W net is actually 40% of the heat supplied. So the heat supplied should be 600 divided by 40 multiplied by 100. Okay. So what is your answer to that? So your answer should be like this. So the assumptions that you make are, you think the plant is steady, heat losses are negligible, so your isothermal is 0.4. So your isothermal should be W net over QH. So your W net is 400. So when your QH is 1,500 megawatts. So that's 1,500 megawatts. So 1,500 and 600 minus 600 is equal to 900. So 900 is your heat lost. So this is due to the heat lost due to the surroundings. Okay. Then you have what you call the Kelvin-Planck statement. So no process is possible whose result is the absorption of heat from reservoir and the conversion of this heat to work. So what this means is no process will be able to produce a W net that is equal to QH. So this can never be 1,500. Now this is 1,500. This can never be 1,500. This has to be less than 1,500. So that's what Kelvin and Planck said. Okay. So then the question arises, why we can't keep the energy rejected? Okay. So look at this example. So you have an energy source at 100 degrees Celsius and a gas at say 25 degrees Celsius, and so suppose it will give you the energy source will heat it up to 80 degrees Celsius, and you can't. So and it does some work as well when the gas is expanding here. So it does work. So when it comes back, what happens actually is it has lost some energy. So it can, when the 80 degrees Celsius gas, when it comes back to 25 degrees Celsius, it will reject heat to the energy source back again. But that is not the same 100 kilojoules that was given. It has used some 15 kilojoules to do the work. Okay. So it has to. So now this concept is not true. Okay. So what happens is this will bring down. So you only need an energy sink for that. So you can't. So this can't happen. So you can't convert everything that has taken from here to work. Okay. So this can happen. So this is what will happen. So Kelvin-Planck said it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. So that is what it is. Okay. So that is the Kelvin-Planck statement. So that means no process is possible whose sole result is the absorption of heat from a reservoir and the conversion of this heat into work. Okay. So you can't have this. Your W net can't be equal to QH. W net has to be less than QH. So even under ideal conditions, the heat engine must reject heat to operate. So we will go about talking about refrigerators as well slightly, so that a refrigerator works on a reverse cycle, reverse heat engine cycle basically. So what a refrigerator does is, now, if for example, if you want, now we talked about okay, we'll go back a little bit here. No, not here. Right here. Now this is your heat engine. So suppose you really want to transfer heat from a cold reservoir, cold place to a hot place, a cold reservoir to a hot reservoir. What you have to do is you need, now when heat transfers from a hot reservoir to a cold reservoir, there will be work rejected. So you need to do some work on the engine for you to transfer a certain amount of heat to the to a hot reservoir. Okay, so you can transfer heat from a cold reservoir to a hot reservoir, but you need to do work on the engine. So this engine is not an engine; it's called a reversed engine, or a heat pump, or a refrigerator. So this shows you what a refrigerator has. So you have an evaporator and a condenser. So if you talk about your domestic refrigerator, you have an evaporator, which is the inside of the fridge, and a condenser, that is the heat, that is the condenser outside of the refrigerator. Some of the refrigerators you can see the condenser coils, and then you have a compressor which compresses the working fluid here, and then you have what you call a throttle valve, which throttles down the condenser, the liquid out of the condenser to the evaporator pressure. So it works at a higher and a low pressure. So it works between condenser pressure and the evaporator pressure. So the liquid is the working fluid rather is throttled from condenser pressure to the evaporator pressure, which in which process it cools down as well. So for this to work, you have to have work input. You have to have work input. So that's your work in, which is the compressor work that you do. And the heat is rejected from the condenser, and heat is absorbed from the evaporator. So the coefficient, then we define the useful work and heat. So if you are using a condenser, if you are using the condenser or a heat pump, if you use the useful energy from the hot reservoir, your coefficient of performance is your QH divided by the work in. So that can be more than 1. That is always more than 1 if it is a heat pump. And for a refrigerator, your useful work is the heat that has been absorbed by the evaporator. So that's so your coefficient of performance, if it is a refrigerator, should be QL divided by WN. Okay. So this explains you that. So COP is the desired output and the required input. So for a refrigerator, so your COP is QL over WN. So see QL. So here you can always say your QH is equal to QL plus WN. Therefore, you can replace your W in by QH minus QL. So that your COP must be 1 over QH, 1 over QH over QL minus 1. And then for a heat pump, your desired output is QH. Therefore, your COP should be QH divided by W in. QH divided by W in, and you know W in is QH minus QL. Therefore, you can replace that with QH minus QL, and you can divide everything by QH. So with that, you can get 1. COP becomes 1 over 1 minus QL over QH. Okay. So this can always be greater than 1. Okay, but it can be less than 1, but it can always be greater than 1. So for heat pumps, it should always be greater than 1. So suppose you have a heat pump that uses 200 joules to work to remove 300 joules of heat from a lower temperature reservoir. How much heat would be delivered to the higher temperature reservoir? So this is a fairly easy, quick example. Okay, it should be 500. Okay, it should be 500. So it's easy. So so the work in is 200. So it will remove 300. So what your Q out should be that 200 plus 300, which is 500 here. And then you have what you again we talk about the closest statement. So it is impossible to construct a device that operates in a cycle and produces no other effect other than heat transfer from a low temperature body to a higher temperature body. So Clausius said that our work into a heat pump or a refrigerator can't be zero. So it's natural phenomenon. It's a natural phenomenon that heat cannot flow from a cold object to a hot object naturally. So then so both Kelvin, Planck, and Clausius statements can explain the second law of thermodynamics. So there are devices that could violate the second law of thermodynamics. So in this example, you have a heat engine that draws that draws energy from a hot reservoir, does some work, and it should reject some QL to here lower temperature reservoir. And suppose you get the same QL and that QH which is equal to QH, and pump up the higher temperature reservoir with QH plus QL. So that cannot happen. Now this is this violates the second law of thermodynamics. So this is what you are trying to say here is you can have a perpetual motion machine of the second kind. So this can't have a 100% efficiency. Okay. So this can't have 100% efficiency. So if something like this works, it means that you draw some heat from a cold reservoir to a hot reservoir, and it doesn't take any work out of it. No, that can't happen. So if something violates the first law of thermodynamics, you say it's a perpetual motion machine of the first kind, and if it violates the second law of thermodynamics, you say perpetual machine of the second kind. So there's a question for you, so you can think what this means. So what is meant by this diagram? So what I have is I have a boiler system, okay, and from the boiler I have a heater So and I have a generator as well. So then the generator is some work to and the generator works. The turbine drives the generator, and the generator does some work out, and some of then it hits it rejects heat to the heater and the boiler. So will that happen? This is actually a perpetual motion of first kind. So if you take the heat amounts, that will not work. So this is another example of the second kind perpetual motion machine of the second kind. So you have a boiler, you have a pump. So this is a boiler pump system. So and then you have a generator, and which does W net without any rejection of heat. Okay. Then you have what you call a Carnot cycle. So Carnot cycle is the ideal cycle, or the maximum, the cycle with the maximum efficiency. So suppose you have a energy source at T hot temperature, which is so. If you do a PV diagram, so the Carnot cycle will operate on a constant isothermal heat absorption and reversible adiabatic heat reversible adiabatic work done, and then reversible isothermal heat heat rejection and reversible adiabatic work done into the system. Okay, so so the first one is constant temperature heat addition. So second, so 2 to 3, constant entropy workout, and 3 is constant temperature heat rejection, and 4 is constant entropy work done. Okay. So this is very important. The efficiency of a reversible heat engine is always less than the efficiency of a reversible engine operating between the same two reservoirs. So that means that if you have a hot reservoir and a cold reservoir, any engine that would work between those hot and cold reservoirs can have a maximum efficiency. So that efficiency doesn't change, whatever the heat amount drawn. Okay. So suppose you have a reversible heat engine and an irreversible heat engine. So your reversible heat engine should have the maximum efficiency. The irreversible heat efficiency. So that is a reversible engine. That's a reversible engine. This is an irreversible engine. So this is the other way around it. So there is a concept of thermodynamic temperature. So thermodynamic temperature means if you have a hot reservoir and a cold reservoir, so the amount of heat that can be drawn from the hot reservoir and the cold reservoir, the hot temperature and hot reservoir and the cold reservoir are proportional to the temperature. So basically, the amount of heat is going to be proportional to the temperatures. That means, so if you have two engines like this, so you have a higher temperature reservoir and a lower temperature reservoir, and you have one engine operating between the higher temperature reservoir and the lower temperature reservoir, and then you have another one operating between an intermediate temperature. So the works here, the addition of those two work should be equal to that. So that's what it says basically. So basically, you can say that you are not supposed. You can know the proof, but what it means is if you have a temperature and if you have a heat amount, so the amount of heat that can be drawn is proportional to the amount of is to the temperature there. So that means there is an absolute zero of temperature. So the absolute zero of temperature is at minus 273 Kelvin. So Carnot efficiency is eta thermal is 1 minus QL over TH, Q1 minus QL over TH, and you can replace for a common Carnot engine QL with QL with TL and QH with TH. Okay, so that is Q. So your thermal efficiency is 1 minus TL over TH. So that temperature divided by that temperature. Yeah. So that's the Carnot efficiency. That's the maximum efficiency that a heat engine can have. And these temperatures always should be written in absolute terms. That means in Kelvin, not Celsius, in Kelvin. So the higher the temperature, the higher the hot reservoir temperature, the higher the efficiency, always. Yeah. So you can calculate the efficiencies for these ones. So you can apply the equation before, which is 1 minus TL over TH is the efficiency. Okay, so here your efficiency of this engine should be 1 minus TL 293 over 350, and this should be 1 minus 293 divided by 1500. So you will see that your efficiencies are so they will give you a similar amount of work, but the efficiencies are not the same. So efficiencies, one has efficiency of 0.8, the other one has an efficiency of 0.13. Then you have what you call entropy. Entropy is cyclical integration of delta Q over T. So that has to be less than 0 or equal to 0. Okay. So this is expressed expressed mathematically, so on. So cyclic integral of delta Q over T is now you integrate Q over T around the cycle. So you have to apply it for the boiler, apply it to the turbine, apply it to the condenser, and apply it to the pump. Then when you do that and add them together, you will always receive a value less than or equal to 0. So that can again be proved. So you can say for a reversible cycle, delta Q over cyclic integral of Q over T, delta Q over T is equal to 0. For an irreversible cycle, this has to be less than 0. Okay. Therefore, it is true. So if it is more than 0, you will always see that it is not true. So entropy during any process will increase. Okay. The entropy of the after the process should always be should be greater than entropy before the start of the process. So you can say for any process, if you integrate from first process to the second process, delta Q over T, you will see that your delta S, the change in entropy, has increased. So delta S is greater than 0 for irreversible process, is equal to 0 for reversible process, and impossible for an less than 0 is it will be it will the it is an impossible process. Okay. So applications of entropy. So when you have a hot body and a cold body, so the entropy of the hot bar will increase. The entropy of the cold bar, the entropy of the hot bar will decrease, and entropy of the cold bar will increase. But the entropy of the whole thing will have increased overall. Okay. So when entropy increases, in the whatever we do in the universe, the entropy is going to increase in the entropy of the universe is increasing all the time, but it doesn't come to the maximum value. So after it has reached the maximum entropy state, so no process can happen thereafter. So for constant volume process, S2 minus S1, so you have first state, second state. You can always say, so delta Q can be stated as MCV delta T. Therefore, S2 minus S1 is equal to MCV ln T2 over T1. Okay. So for constant volume process. So solid objects are constant volume processes. So if this happens in a solid object, so that is how you define entropy. So entropy leads to TS diagrams and PV diagrams. There is no change in entropy during a process. So if there is no change in entropy in the process, we call it an isentropic process. So the entropy leads to properties like TS and TS, HS, and in addition to PV diagram. So in an isentropic process, your S hasn't changed. Okay, so that's why they are important. So we have talked about today. We have talked about describe the operation between heat engines, try to understand the Kelvin Planck statements, and Carnot cycle, and thermodynamic temperature, thermodynamic cycles, and we defined entropy. Now what you have to do now is go and look at the tutorial and try and work out the tutorial. So we will do that next Wednesday during the tutorial class, and we will also look at this lecture again during on Thursday, and I can entertain your questions on Thursday afternoon. And thank you for listening. So I'll see you next week on Wednesday.